Hi, this is Luke from the Stats Medic, and in this video we're going to talk about significance tests for slope. Now we only have one learning target here, and that's to perform a significance test about the slope beta of the population regression line, and we're going to do that using the familiar four-step process. So you can expect to see state, plan, do, conclude. So let's take a look at the context for the activity for this lesson. The question to be answered here is, how does GPA relate to ACT score? Now, the first thing that you have to know about the ACT test is that it is a test that will give a student a score somewhere between 1 and 36. So a 36 would be a perfect score. So let's look at the setup of the problem here. It says a teacher is wondering if there is a relationship between GPA and ACT score. She took a random sample of 9 out of her 101 students and recorded their GPA and ACT score. The data are below. So we have the data for the 9 students that were randomly selected, and then you'll even see below here that you're not going to need any technology in order to make the graphs because those are provided for you here. So the first page is mostly just that information with a couple of questions. And then if you look at the second page of the activity, this is where we'll get into the four-step significance test with state, plan, do, conclude. So you have everything that you need in order to complete this activity. You'll notice the stop sign here after you finish your conclusion from the significance test. So you're going to go ahead and work all the way through the activity and then come back to check your answers. So go ahead and pause the video now. So let's take a look at your answers from the activity. In question number 1, I was hoping that you would predict that there would be a positive linear relationship here. It seems to make sense that as a student's GPA goes up, that they would tend to do better on the ACT score. And then that's actually confirmed when you look down here at the scatter plot that we do see a positive linear relationship. Now let's jump into the computer output to make sure that we understand each one of the values that's being given to us here. The first thing to recognize is that this is always going to be the X variable in the computer output, and you can verify that by looking at the scatter plot where GPA is the X variable. And then the next two things that you need, this right here is your A value, which is the y-intercept, and the value below that is the B value, which is the slope, and of course that's the value that we're going to need for doing our significance test. And then if you move over to the next column, the value that we're definitely going to need for this is the standard error of the slope. This is SEB. So make sure you identify the values that we're going to need later. Now that helps you, of course, with question number 2, because you need your y-intercept here, 1.201, and you need your slope here, 7.507. Now check to make sure that you are in fact using contextual variables instead of x and y, and then also check to make sure that you are making the predicted ACT score there. Now let's see what we have for the full four-step significance test. So starting with the state, we need to first identify the parameter. So check to make sure that you've used the correct notation here, beta, which is the true slope of the population LSRL for GPA and ACT. This is where we'll put in our context of the problem. Now for the null hypothesis, we're going to say that that true slope of the population LSRL is equal to 0. And if there is a 0 slope here, what that's really telling us is that there is no linear relationship. So let's just go ahead and add that in. In words, this null hypothesis is telling us that there is no linear relationship. Now for the alternative hypothesis, we have to decide whether it is one-sided or two-sided. And there's always going to be a clue in the wording of the question. So if we look back at the wording of the question, we'll notice that we're looking for evidence of a positive linear relationship. So that's telling you that your alternative hypothesis is one-sided and should be greater than 0. And in words, what this alternative hypothesis is telling us is that there is a positive linear relationship. If we move over to the statistic, we got this, of course, from the computer output. That is the slope of the sample regression line. And then for the alpha level, since we weren't given a value, we'll go to the default value of 0.05. So let's move on to the plan. So first, you have to name the procedure, which is a one-sample t-test for slope. And then we have to jump into checking 5 conditions here. Now remember, the way that you will recall the 5 conditions is by using the LINER acronym here. So let's go ahead and check each one of the 5 conditions. The first condition is the linear condition, and there's really 2 different ways that you could check this. One, you could check that the scatter plot is fairly linear, or you could check that the residual plot shows no pattern. So if we look back here, the scatter plot definitely appears to be fairly linear. And then if we look at the residual plot, there's no clear leftover pattern of a U-shape or an upside down U-shape in the residual plot. So we're going to go ahead and say that the linear condition is satisfied. Now, for the independent condition, there are 2 things that we need to check here. The first is that because we are sampling without replacement, we need to check the 10% condition here, that the sample is less than 10% of the population. And then we should also state that each one of the individual observations are independent. In other words, one student's ACT score does not have an impact on another. So we'll say that the independent condition is satisfied. For the normal condition, we need to take a look at the dot plot of the residuals, okay? Not the residual plot, the dot plot of residuals. So if we look at the dot plot of residuals here, we're trying to check if there's strong skew or outliers. Now, I was a bit concerned about this value here, but I went ahead and checked using the outlier rule, and it was not considered an outlier. So we're going to go ahead and say that the normal condition is satisfied. For equal standard deviation, we go back to the residual plot, and we want to see that there's similar variability for each x value. So in the residual plot, for each x value, it appears that we have fairly similar variability as we move through each of the x values here. So we're going to go ahead and say that the equal standard deviation condition is satisfied. And then the last condition, the random one, we were told in the setup of the problem that the teacher was taking a random sample of 9 students. So now that we've checked our 5 conditions, we are ready to do some calculations here. So the general formula is something that you're hopefully very familiar with at this point in the course. We're going to do statistic minus parameter over standard deviation. But you had to come up with the specific formula on your own. Now we know that this is going to be a t-test statistic because in the last lesson for confidence intervals we used t-star. And our statistic here is our slope from our sample, and our parameter is the slope for the population. And then we're going to divide that by the standard deviation, which we are estimating using the standard error of b. So our calculation, if you look here, we just have to plug in our values, which we got from the computer output on the previous page. This is our b, this is our standard error of b, and that leads us to our t-test statistic. Now let's check what that looks like in the picture here. And I want to try to explain why we have 2 different pictures here. The first picture is the sampling distribution of b, the sample slopes. And it is approximately normal. And we know, because we're assuming the null hypothesis is true, that the mean should be 0. Now, the standard deviation of this technically is sigma of b, which we don't know. And what we're going to do is we're going to estimate that sigma of b using SEB. But in doing so, we're actually transforming the normal distribution into a t-distribution. And so when we standardize, and it's at the point where we standardize, this is when the normal distribution turns into a t-distribution. And recall, our degrees of freedom here is n minus 2, which in this case, 9 minus 2, is going to give us our degrees of freedom of 7. And so you'll notice here, this is where we're putting our standardized test statistic, 5.819. I try to train my students to put a box around the test statistic and a box around the p-value. And the reason is because at the end of the year at the AP exam, this is something that will definitely be on the rubric. So we got a very, very small p-value that you can see here. And that's going to help us with our conclusion. And so you'll notice the conclusion has 2 parts. In the first part here, all we're doing is we're interpreting that p-value. So let's look at this interpretation of the p-value. It says, assuming the null is true, there is a, now here's your p-value, probability of getting a sample slope b of 7.507 or greater purely by chance. Now what we're really doing there is we're just explaining this shaded red region in the normal distribution up here. Now that we have interpreted the p-value, this is where we can go ahead and make our decision about what we're going to do with that p-value. And because that p-value is very much smaller than our alpha level, we are going to reject the null hypothesis, and we do have convincing evidence of a positive linear relationship between GPA and ACT. So you need to make sure that at the very end of your conclusion, you are talking about the alternative hypothesis here, and you are doing that in the context of the problem. So let's see if we can summarize our learning here in the important ideas. So we only have one learning target here, and that's to be able to do a significance test for slope, but we know we want to do that with the four-step process, so let's go ahead and highlight what needs to be included in each part of the four-step process. So in the state, we would start by identifying the parameter beta, which is going to be the true slope of the population LSRL for, and then we'd put our context in here for X and for Y. And then we would use that parameter to set up our hypotheses. And the null hypothesis is always going to say beta equals 0, which would say that there is no linear relationship between the two variables. And then the alternative could be one-sided or two-sided, so it could be beta is greater than 0, or beta is less than 0, or beta is not equal to 0. And then the other two things that we would include in the state is the statistic based on our sample, so the sample slope of the regression line, and then the alpha level. Now for the plan, we would start by identifying the name of the procedure, and this is called a one-sample t-test for slope. And then we would go ahead and check all 5 of the conditions necessary for inference for slope, which is linear. And I'm just going to say see previous lesson if you want to know how to check all 5 of those conditions. And then we move to the do part. And here we would start with our general formula for a test statistic. And we know that this is the statistic minus the parameter, all divided by the standard deviation of the statistic. And now the specific formula for testing for slopes would be that it is a t-test statistic. And we take our statistic, which is b, minus our parameter, which is beta, which will be 0 according to the null hypothesis. And then we divide that by the standard error of b. Now one thing to remember here is the degrees of freedom is n minus 2. And then I am going to make a little note here of what we had to do in order to calculate our p-value in the previous activity, which is to use the tcdf command on the calculator. And the way the tcdf command works is that you have to tell the calculator the lower value, the upper value, and then the degrees of freedom. And that will allow you to get your p-value. And then, of course, with the do, you're going to include the 2 pictures, the unstandardized as well as the standardized. Now, for the conclude, I hope at this point in the course, we are very familiar writing a conclusion for a significance test. So let's move to the check your understanding and see if you can apply this learning in a new context. So go ahead and try the check your understanding problem on your own and then come back to the video to check your answers. So go ahead and pause the video now. So let's see how you did on the check your understanding problem. So hopefully you first took a look at the computer output to identify the values that you were going to need for the significance test. So looking at the computer output here, the first value that we know we're going to need is the slope of the sample regression line, b, and then right next to that is the standard error of that slope, which we're going to need for our significance test. Those are the 2 important values we're going to need to carry down. So let's check into the state, and starting with the parameter, make sure you've used the correct notation here and that you've included some context of the 2 variables that we're measuring here. The null hypothesis is definitely always going to be beta is equal to 0. And then the alternative, we're saying beta is greater than 0, and that's because of the wording of the question. If you look back, it said, does it provide convincing evidence of a positive linear relationship? So we know the alternative is going to be one-sided. We grabbed the sample slope from the computer output, and then they also told us the alpha level was 0.05 here. Now for the plan, we first identified the type of inference procedure, one sample t-test for slope. And very lucky for us here, there was something very important in the question here, which says that assume the conditions have been met, which means that we don't have to check the 5 conditions for liner. Now this is often the case on the AP exam if there is going to be a question about inference for slope. So I've just made note of the fact that this was given to us in the problem. Now for the do, check to make sure that you have your general formula here and your specific formula, and then your numbers plugged in, and of course you should get a t-test statistic of about 3.07. So I've shown 2 pictures. First, the unstandardized picture, the normal distribution, as well as the standardized picture, which is a t-distribution, and here's where I've identified the degrees of freedom as being 36. And then I put in a box here the t-test statistic, as well as the p-value. Now, quick note here. If you look at the t-test statistic of 3.07, I wonder if you noticed that this was also given to you in the computer output. So the computer output is in fact doing a significance test and calculating the test statistic for you. Now if you move over one more column, it would seem that the p-value here should match with the p-value in the computer output, but it does not. And you'll notice that our p-value is exactly 1/2 of their p-value. And here's the reason. Anytime you are given computer output will always calculate the p-value based on a 2-sided test. So we're going to say computer output gives p-value based on a 2-sided test. And since we're only doing a 1-sided test here, it makes sense that our p-value is 1/2 of what's given in the computer output. So in the conclusion here, let's check a couple of things. Assuming the null is true, there is and here's your p-value, 0.002 probability of getting a sample slope of 1.4929 or greater. Check to make sure you have your or greater, purely by chance. Because our p-value is less than the alpha value, we will reject the null hypothesis, and we do have convincing evidence of the alternative, which says that there is a positive linear relationship between count of crying peaks and IQ in the population of infants. So this concludes our lesson on the significance test for slope.